study about the signal diagram of 8085 microprocessor. So let's start with our topic. Let us first draw the diagram and then we will study all the signals of 8085. So this is the complete signal diagram of 8085. All the signals in the 8085, they are divided into six categories. We have the address bus, the data bus, control and status signals. Then we have serial input output signals, externally initiated signals, and power supply and frequency signals. These are the power supplies and the frequency signals above. So all the signals in the 8085, they are divided into these six categories. So these are the six groups into which all the signals are divided. You can see that we have the address bus from the pins 28 to 21 and from 12 to 19. And this lower order address bus, it is multiplexed with the data bus. And it is denoted as AD0 to AD7. There are the 8 bits of the data bus, and the lower order address bus also is there, and we have 8 bits for the higher order address bus. These are the power supply and the frequency signals. X1 and X2 here at pin number 1 and 2, the crystal is connected, which is providing the clock frequency to the 8085 microprocessor. Then we have the plus 5 volts power supply, and this is the ground connection. Then we have the control and the status signals. These are the control and status signals from pin number 30, 29, 33, 34, 32 and 31. ALE, that is address latch enable. Then S0 and S1 are the status signals. IO, that is input, output and memory. Then read and write. So these are the control and status signals. Then we have reset out and clock out. Clock out is again the frequency signal, and reset out is the external signal. Then we have ready, hold, reset in, INT, A bar, HLDA. These are the external signal acknowledgement signals. That is in respect to the these external signals, the acknowledgement signal which is produced by the 8085, these are the external signals acknowledgement. Then from pin number 6 to 10, we have the externally initiated signals trap, RST 7.5, 6.5, 5.5 and INT-R. Then we have on pin number 4 and 5 the serial input output signals. SID is the serial input signal and SOD is the serial output signal. So this is how all the signals of 8085, they are classified into the 6 groups. So these signals of 8085, they are classified in these 6 categories. So let us study all the signals one by one. First, we will start with the address and the data buses. The address bus of 8085 microprocessor, it is a 16-bit bus and it is a unidirectional bus. These 16 bits, they are denoted from A0 to A15 and divided into two parts: lower order address bus and higher order address bus. The lower order address bus, because it is 16 bits, so it is divided into 8 and 8 bits. The lower order address bus, it is of 8 bits starting from A0 to A7. And the higher order address bus, it is also of 8 bits starting from A8 to A15. Okay. Now this bus, it is unidirectional. And the lower order address bus, it is multiplexed with the data bus. The data bus, it is of 8 bits and it is denoted by D0 to D7. As it is multiplexed with the lower order address bus, so the multiplexed address and data bus, they are denoted as AD0 to AD7. This is the multiplexed address and the data bus. So these were the address and the data buses of 8085. Now we have the control and the status signals. The control and the status signals, they provide the controlling of the functions of the 8085. Here we have ALE, RD bar, WR bar, these are the 5 control and the status signals. The full form of ALE is address latch enable. This signal is used when we want to demultiplex the address and the data buses. When this signal is active, that is its power, it is equal to 1, because it is an active high signal. So when its value is 1 or it is active, it means that on the address and the data bus, the multiplex address and the data bus, it is having the address of the memory. So this signal is used in the demultiplexing of the address and the data buses. Then we have RD bar, it is the read control signal. This is an active low signal. A signal having bar on it, it means that it is an active low signal. It means it is active when its value is equals to 0. When this signal is low or it is active, it means that the microprocessor, it is currently performing the read operation. Then we have write control signal. This signal is also an active low signal. And when its value is equal to 0 or it is active, it means that the microprocessor, it is currently performing the write operation. Means it is writing the instructions or the data into either the memory or the input output devices. Then we have input output and memory signal. Now when this signal is active, that is its value is equals to 1, it means that it is an input output operation. And when its value is equals to 0, it means that it is a memory operation. 0 means it is a memory operation and 1 means it is an input output operation. Suppose we have the read signal as an active and we have input output signal as 1. It means that the microprocessor, it is currently performing the read operation on the input output devices. Now if the read signal is low and this signal is also low, it means it is a memory operation. So the microprocessor, it is currently performing the read operation of the memory. So in this way the signals have been defined. The operations of the microprocessor, like it's either a memory read operation, memory write operation, or input output read or input output write operations. So these three signals defines the operations of the microprocessor. Then we have S1 and S0. These are the status signals. Status signals also define the current state of the microprocessor. That what is the current state, what is the function which is the microprocessor is currently performing. When S1 and S0, they are 0, 0, 0, 1, 1, 0 and 1, 1. 0, 0 means that it is a halt state. 0, 1 means that it is a write operation. 1, 0 means it is a read operation and 1, 1 means it is the fetch operation. So this is how the operations of the microprocessor are being defined. These are the states of the microprocessor. What is the current state of the microprocessor? It is defined by these status signals. So these 5 signals, these are the control and the status signals of 8085. Next we have the externally initiated signals. The next category of signal is the externally initiated and interrupt signals, and in this we have the various signals. First we have reset in. Reset pin, it is an active low signal. It means it is active when its value is equals to 0. Now when this signal is low, that means it is active. So the microprocessor is reset. Reset means the program counter, it is set to 0. All the contents of the program counter, they are equal to 0. It means we have just bring it to its initial position. The buses are tri-stated. All the buses, address bus, data bus, control buses, they go in the tri-state state. So this reset in, what it actually does, it brings the microprocessor to its initial condition, reset it and make all the values equal to 0. Next signal we have is reset out. Reset out, it is an active high signal. This signal indicates that the processor is being reset. When the signal, when we are giving this signal reset in, we are resetting the microprocessor. We are making all the values equals to 0. And when the microprocessor has been reset, it will send this signal reset out, and it will show that the processor has been reset. And the signal is also used to reset other devices. The other devices which are connected to the microprocessor, like the peripheral devices or any devices which is interfaced with the microprocessor, they can be reset using this signal. So this signal, it is a coming out signal or of the microprocessor, that is coming out of the 8085, and it can be sent to other devices to reset them. Also, it can be made high to show that the microprocessor, it is in the reset condition. Next signal we have is ready. There are sometimes some cases when we have to interface some of the devices with the microprocessor so that it can be used in certain applications. Now, when these devices, they are interfaced with the microprocessor, it may happen that the speed of the microprocessor is very fast, but the device which is connected to it, it is very slow in operation. So there is some misunderstanding that when the microprocessor is working and the device which is connected to it, it is responding very slow. So to synchronize the working of the interfaced device and the microprocessor, this signal ready is used. Now, when this signal is low, the processor waits for the integral number of clock cycles. It shows that the interfaced device which is connected to the microprocessor, it is not in a ready condition. It is synchronizing, or it is coming towards or making up with the microprocessor to come in with the come with the speed, or have some response with the microprocessor. So the microprocessor waits for the device. When the device comes to the same speed as that of the microprocessor, then this signal ready goes high. When the signal is high, it means that the microprocessor and the peripheral device, it is ready for communication, and then you can send or you can receive the data, or you can exchange the contents between the device and the microprocessor. So this ready signal, it is an active high signal. When the signal is high, it means that the microprocessor and the device, they are ready for the communication. When the signal is low, then the microprocessor, it will wait for the integral number of clock cycles so that the device, it can make up with the speed of the microprocessor. The next signal we have is hold. This signal hold, it indicates that a peripheral device like DMA is what? Direct memory access. It's a kind of peripheral device which is interfaced with the 8085. DMA controller, it is requesting the use of the address and the data bus. When this peripheral device DMA, it is connected to the microprocessor, it wants to use the address and the data bus of the 8085 for the communication or the transfer of data. So this DMA, it sends a signal hold, and when this signal is active high, that means its value is equals to 1. When the signal is sent by the DMA to the microprocessor, it means that the DMA, it is requesting to use the address and the data bus of 8085. Now, when the DMA, it sends this hold signal, so in respect to it, the 8085 microprocessor, it also sends the signal HLDA. HLDA means hold acknowledgement. Its full form is hold acknowledgement. So this signal HLDA shows that the microprocessor, it has released its control over the address and the data buses, and the address and the data buses, they can now be used by the DMA. So the DMA, it sends a signal hold to the microprocessor requesting for the use of the address and the data bus, and with respect to this, the microprocessor, it again sends a signal HLDA, that is hold acknowledgement, to show the DMA that it has released the control over the buses, and now the buses, they can be used by the DMA. Okay. Next we have INTR. It is interrupt request. Interrupt is the word defined interrupt, that it is a kind of disturbance. When you are, like, suppose you are doing something, you are in the middle of something, doing some work, and your friend comes and he wants that, please, I want to interrupt you, or I want to disturb you. So this is in the same way. When the microprocessor, it is currently doing some operations, any type of operations it is doing, suppose like any arithmetic or logical operation it is performing, and in middle of it, any peripheral device or any device, it wants to disturb the microprocessor in middle of its current operation, then he sends an interrupt to the 8085 microprocessor. And these disturbance or these signals which are given by the peripheral devices to the microprocessor, they are called the interrupt signal. So they are just like disturbing the 8085. And this INTR, it is also a kind of interrupt. It is a general purpose interrupt which is used by any peripheral device which is connected to 8085. Now, with respect to INTR, because INTR was an interrupt request which a device is sending to the microprocessor. So, in response to it, the microprocessor, it is going to send another signal, and this signal is INTA bar. This is interrupt acknowledgement. This means that when the device, it is sending, suppose it is our microprocessor 8085, and it is a peripheral device or any device which is interfaced with it. Now this device, it want to interrupt the 8085, so this device is going to send the signal INTR, that is, it is requesting to interrupt the 8085, and with respect to it, 8085 will send the signal INTA, that is interrupt acknowledge, that he has received the request and he is acknowledging the device, or he is allowing the device to interface or interrupt the 8085. So this is just in response to the interrupt request generated. Then we have RST 7.5, RST 6.5 and RST 5.5. These three are also a type of interrupts. RST means restart. These are the three types of restart interrupts. These interrupts are vectored interrupts. Means these interrupts are already defined. Vectored means they have a program which is returned at a certain location. Whenever this type of interrupt is given to the 8085, then the interrupt it jumps to that memory location, and on that memory location whatever program is written, the microprocessor start executing that program. So currently the microprocessor it is doing some work. Whenever this type of vectored interrupt is given, then microprocessor it will stop its current operation and then jumps to that location which is defined by each of these interrupts, and at that memory location a program has been written, and the microprocessor stops its operation and start executing that program. So it is a kind of interrupt, stopping its current operation and doing some other work. Next we have trap. Trap is also a kind of interrupt, but it is a non-maskable interrupt, and it is having highest priority. Non-maskable means there are two types of interrupts: maskable, non-maskable. Maskable means that they can be masked. The microprocessor, if it is given a maskable interrupt, then the microprocessor it can complete its current operation and then it can acknowledge the interrupt. But non-maskable means that whenever this type of interrupt is given, microprocessor has to stop its current operation and acknowledge this trap interrupt. So this cannot be masked, and whenever all if all the interrupts they are simultaneously given to the microprocessor, then trap has to be first acknowledged because it has the highest priority. We are going to discuss the interrupts further in details in our later videos. Here we have just given a brief idea that what are these interrupts. So these were our externally initiated and interrupt signals. The next type of signals are serial input-output signals. There are two serial input-output signals, SID and SOD. SID is serial input signal, and SOD is serial output signal. This serial input signal, it means that the data which is available on the line address or on the data bus, it is an input data. So serial input signal, it means that whatever bit is available on this line, whether it is 0 or whether it is 1, this bit it is loaded into the D7 bit of the register A. A is our accumulator. So accumulator, it is an 8-bit register. It will be having D0 to D7. This is our accumulator. So bit on this line, it will be loaded to the D7 bit of register A. Suppose we have 0 here, so on D7 we will get 0, and if it has 1, then D7 bit will become 1 of the accumulator. And how this bit is becoming 0 or 1, we are using the RIM instruction. RIM instruction is read, interrupt, mask. This instruction is used to load this bit into the D7 bit of the register A. Now we have SOD, that is serial output signal. This signal is So this signal SOD, it is set or reset. Set means its value is becoming 1 and reset means its value is becoming 0. So it is set or reset by using the SIM instruction. SIM is set interrupt mask. We are going to use this RIM and SIM instructions to set or reset these SID and SOD signal. So whenever the microprocessor it is performing the serial input output communication, then these signals SID and SOD are used. Next, we have the power supply and the clock frequency signals. These four are the power supply and clock frequency signals. VCC is at plus 5 volt power supply. We know that the 8085 it uses plus 5 volt power supply. So this plus 5 volt it is connected at the point VCC. VSS it is the ground reference. The system ground is connected here. So this is the ground signal. X1 and X2 we have connected here the crystal having frequency of 6 megahertz. Now the clock frequency of the 8085 it is 3.125 megahertz. Approximately it is 3.125 megahertz. So this crystal we are connected, it is just double the clock frequency, because the connections inside the pin 1 and 2 we have a flip-flop, JK flip-flop, and this JK flip-flop it divides the crystal frequency by 2. So we are connecting the crystal of frequency 6 megahertz, it will be divided by 2, so it become approximately 3.125 megahertz. So this is the clock frequency at which the 8085 microprocessor works. Then we have the clock. This is the clock output. This signal is the clock pulse. Whenever the microprocessor wants to give a clock pulse to any device, this is the output of the clock pulse. So these were the 6 categories in which all the signals of the 8085 are divided. First, we studied about the address bus and the data bus. Then we have the control and the status signals. Then externally initiated and interrupt signals. Then we studied the serial input output signals, and in the last we studied about the power supply and clock frequency signals. Now these signals they can be represented completely on the pin diagram, can also be represented in the same diagram. These 1, 2, 3 these are the pins and these are the input and the output signals. So this was the complete signal diagram and its description of 8085. So I hope this topic is clear to you.